Hi, everyone.
Hello, hello. Thanks for joining us today.
Got a lot of people coming in here. Awesome. Okay, we'll take another minute or two to get started here, and then we'll get going just while everybody trickles in. I hope everybody's having a nice day. If you guys want, put it up in the chat. Love to hear your where you're from, your name, where you're from, what you do for work. That'd be awesome to hear. I'll start.
All right, I think we're good to start.
Awesome.
Okay. Hello, everybody. Happy Wednesday. Appreciate everyone joining in. If you got we got a few people joining us so far, so welcome to another month, another installment of Clear Calcs Learn Hour. A friendly reminder as you're joining, go ahead and mute yourself if you can. And of course, if we are at a point where we're asking questions, doing a little bit of a Q&A and back and forth throughout the webinar, we'll definitely ask you to unmute yourself so that it could be a bit more collaborative. As you're going through these a couple of introduction slides, again, as Laurent mentioned, feel free to say hello in the chat box. If you guys are familiar with Zoom, go ahead and click that chat. And you can also send your name, your title, whether you're an architect, structural engineer, building designer, permit reviewer, or academic, and just where you're joining us from. For anybody who's going to be, sorry, today we're going to be talking about open web steel joist. We will actually go through that in the next couple of slides. But first, let's talk about a bit about ClearCalcs for those of you who are not familiar or just started with us recently. ClearCalcs is a cloud-based structural calculation software combining together FEA tools with easy-to-use tools for wood, engineered lumber, concrete, steel, cold-formed steel trusses, moment frames, connections, and all that fun stuff. We're aiming to be more accurate. We want to eliminate waste of time. I'd say our most popular feature is our load linking or dynamic load path tracking. So definitely check that out if you guys haven't already. This is one way that we're trying to be more accurate with ClearCalc. So in every one of our calculations, you can expand any input or output field into what we call our debug mode. With our debug mode, you'll get an additional description and then also the code or standard reference that applies to that specific input or output. This next photo is what we call our member selector, where you can come in after you've input your plan length, your supports, your load, your boundary conditions, and then quickly filter through the types of beams that you want, and you can see if they're passing or failing. And finally, I didn't mention it earlier, but ClearCalcs is available everywhere. We are a cloud-based platform, so whether you're at home or at the office, anywhere you got access to your internet, you've got access to ClearCalcs. As you can see, we also give you guys an audit log. So you can, if you're working remotely in a team, you can keep track of who's making what changes in real time. So that way everybody's on the same page. Now I'll just be talking about our Blueprint community. Some of you may be familiar with this already, but we have created a blog space for our users where they can share their ideas, projects, or any questions they may have. This is very much like the engineering forums that you may have seen online. We have created this forum to build a strong ClearCalcs community where we can all learn from each other and share our knowledge. You can easily join with your email. It would take only 5 minutes and add any topics of discussion in this community. We have already a topic of discussion for this webinar available in Blueprint. You can ask your questions by replying to this thread instead of sending it through our support system. This way, your colleagues that may be watching this webinar later can also look at this discussion and add their thoughts as well. If you guys have seen the last webinar, my name is Tara. I'm a structural engineer developer working in the content at ClearCalcs. We also have with us Laurent today, who's going to be our main presenter. He's a professional engineer here at North America, and he is a team lead for our content team. Feel free to send through questions, anything that you might have, comments through the chat, and we'll have a dedicated Q&A section at the end of the webinar. And if it makes sense, though, we might ask you to unmute yourself so that you can ask that from us, and we can do a back and forth. All right, I'm just going to pass this to Laurent.
Okay, thank you, Tara. Thank you, everybody here who's joining our webinar today. Always fun to be doing these, always fun to be sharing what we've learned in our careers. And to be honest, for me, the most fun part is to hear your thoughts, your questions, your comments as we go through this, because always end up coming out a little bit smarter when I started with these webinars. So please put your questions, put your thoughts. You know, if I'm saying something, you're like, oh yeah, I remember seeing this, or like, oh, like I did this project, we did it differently, or something like that. Hey, put that in the chat. Would love to hear your thoughts. I'm happy to discuss at the end of the session as well, and so we can all learn from each other. And I'll repeat the Blueprint community that Tara mentioned. Super excited for that. We've just launched this community. The whole point there is we've got a lot of people using ClearCalcs. Love for, instead of us being always in the way and facilitating communication, what happens if we put everybody in the room together and we just start chatting about ClearCalcs? That's basically what we're hoping to do, and hoping to see that from you all. So please make an account, come join us.
The bridge down there, I'm not sure. I'm not sure the bridge actually shakes.
I think someone forgot to mute there, but all good. Okay, so open web steel joist. Today, what we're going to do, we're going to be talking about steel joist, as you might have guessed. We're going to be thinking about like the different types, what a steel joist is, some of their applications, why we would choose them, some of the challenges with designing with those, and then we're going to look at 2 design examples in our new steel joist calculator in ClearCalcs. So, what are open web steel joists? If you made it this far, you probably have a pretty good idea what they are, but I'm going to just quickly repeat it in case somebody's watching a recording or something. What they are basically trusses, very standardized trusses, very lightweight. Typically, they're used to support floors and roofs in buildings. Odds are you've probably heard these called bar joists as well. I've heard a couple other names. Maybe, you know, if you want, put up in the chat what you typically call these things. I've heard mostly bar joist or open web steel joist, but maybe there's some other names for them out there. Key components for this. Really, when we talk about a steel joist, especially from like the bigger perspective, we've got the top chord, the bottom chord, and then the web or the diagonals. Top chord, bottom chord, that's how it is for a truss. And then again, the diagonals are what take the shear. Biggest, most important thing about these steel joists, they are extremely efficient. As a construction material or solution, they are super efficient. If you think about, say, an I-beam in steel, where your flanges are taking the moment, and then the web is taking the shear, usually it's very rare that, say, an I-beam, your shear is going to govern. So steel joists basically address that by not having a full web and instead just having diagonals. So you save on a lot of metal and you're still able to hold up your loads. So that's the idea with a steel joist. It does bring some challenges as well, which is what we're going to go over today. So when would you want to use a steel joist? Again, if you made it this far, you've probably specified these before, you're thinking about it, you've probably got a bit of an idea, but we'll go over some of this. So the biggest one, you can span really long spans with steel joist, especially when we're talking about LH, DLH series, which we'll get over in a second. You can really go into some long spans. Their lightweight really helps with that as well. And what that translates to, especially if you're looking for open floor plans. So I'm sure we've all been to a Costco or a Walmart or something here, and you look up and you see all these trusses above your head. That's the benefit of these steel joists. They're super light. You can get some really open floors. You can get a lot of open lighting with them. So that's where you see these shine the most. And obviously, again, very efficient members. So you're not putting a whole lot of steel for what you're getting. So that saves you a lot on cost. Now, times where you might not want to use steel joists, so maybe you want just a regular steel beam or other materials. If you've got short spans, typically a regular steel beam or even wood or something like that is probably going to be more economical. If you've got some, crazy architecture or something like that, again, these are pretty standardized products, the steel joist. So once you're going off the standard, it's going to be a little harder to make that work in your building. Not impossible, and a lot of manufacturers out there will work with you, but it might add some complexity to your solution. And then lastly, because as I mentioned, we're dealing with a open web, point loads tend to be a bit trickier with steel joists. They add a bit more shear. We're going to talk a little bit more about that later on, specifically to point loads and non-uniform loads. But when you've got some really heavy point loads, that's a case where your steel joist might not be the best option. Okay, so thinking now about the different types of open web steel joists. So I mentioned it earlier, we've got the K series, LH series, DLH series. These are probably the three most common ones. We've got some historical sections out there. I think I've heard some people talk about SJ series, for instance. These are the three ones that are typically manufactured right now in the US. When you're looking at these, basically K, you're thinking up to about 60-foot spans. In DLH, for instance, these are like the really big ones. We're talking about 6-foot deep trusses going all the way up to almost 150-foot spans. So these are really long. If you're a ClearCalcs user, you might have seen we ran a survey not that long ago about what type of steel joist you're specifying. Overwhelmingly, interestingly, was K series. I'm not sure that surprises anybody here. They are, I guess, the more common spans, but K series by far, LH series. And a surprising amount, I think, of you also responded about historical sections. So that's something that we'll be looking at later on. Big thing here, these are typically resisting uniform loads. So you're thinking about, your 20 PSF dead load, 40 PSF live load, or 100 PSF live load, whatever that might be. Typically, you would be resisting a uniform load with these. Other types of joists here. We're not going to go too much into detail about these two, but I'll highlight them now because they are an important design component. First one, joist girders. So as our joists basically carry those uniform loads, they need to be sitting on something. Sometimes that might be a steel girder. Sometimes that might be a joist girder. And so you've got a picture of that on the right here. These are typically specified in terms of the point loads from the joist reactions. These are much beefier members, but you'd have less of them, obviously, because they're spanning between your columns. Another one that we have as well, and we're seeing more and more usage of those, is the CJ series, which are basically composite joists. So they work compositely with concrete slabs. So typically in floors, you'll see those now for just basically more efficient material use. Again, we're not going to talk too much about these two today. They're out there. If there's something that you design with pretty often, please let us know. And happy to kind of look more deeply into those later. Just to give some examples here of things we can do with steel joists. Like I said, these are pretty standardized product. You can, especially when we're thinking about like roof pitch or something like that, manufacturers will typically be able to accommodate these pitches. So you can see that the different patterns here. You can also see like the standard one is that joist where it's underslung, it's called. So when you've got the top chord being supported, but you could also have, say, with the square ends, if your conditions require you to have that bottom chord supported instead. But some typical things that you might be able to do. If you've done other steel joist types or you've experimented with different shapes, hey, post that in the chat or go on Blueprint and post some pictures of your projects. We'd love to see those. Okay, now we're going to talk about open web steel joists in buildings. So got a nice picture there of a building under construction. Important thing here, these will typically be supporting floor loads and roof loads. They're not going to be, say, taking reactions from another beam typically or something like that. They're really there to purely support the distributed loads. So why you would want a steel joist in the building? The biggest one, I think I'm repeating this enough now, but efficiency. From a strength to weight perspective, like amazing. You're not putting a whole lot of steel and you're getting a whole lot of capacity, a whole lot of long spans with the steel joist. So that's typically the main reason you're going to be putting this in the building. From that, you get some architectural freedom as well. So again, those long spans, if your architect wants some open designs, that's a really good way. You can get, up to 150-foot spans without any columns on these with steel joists, which is about as good as it gets from like a standardized product. And then another one there with the downstream savings. So longer spans, less columns, less footings, less weight, less seismic loads, less lateral demand. All these things add up. They can also add you some savings in a project. Might not be the reason you switch to it, to a steel joist from another solution, but it's something to consider as well. And then other things here for multi-story buildings specifically, again, with these long spans, less columns, more floor space. So we see those a lot more now in multi-story buildings, just because of those long spans and those minimal columns. Other big thing, and this is super convenient, I'm sure a lot of you have seen this, because they have a open web, it makes it very easy to run conduits, HVAC, whatever you might need through the webs. You've got a nice picture of duct going through the webs here. That might save you on some ceiling space. It might make it a bit more aesthetic, whatever you might be looking for. That's a really good benefit with the open web steel joists. And lastly, just because I'm a bit of a structural nerd myself, trusses look kind of cool. We've got more and more architects just putting those now out there in the open, sharing, showing off the structure. You've got an example there of an open web steel joist being used in a facade here, for instance. So if you're looking for that kind of industrial look with your architect, or if you're an architect specifying, that might be a solution there. Okay, we've talked about why you'd put this in. Now let's talk about a bit of the challenges when you're designing with these steel joists. So first one I mentioned earlier, non-uniform loads. So point loads or triangular loads, whatever that might be. That's probably, as a designer, one of the main challenges you'll be facing with a steel joist design. So important thing, if you're dealing with a point load on the cord, so not at a panel point, you have to think about that cord's going to want to bend. And those cords, in a truss, if you're taking, structural analysis or your structural design course, typically your cords or all your members aren't actually seeing any bending. You're assuming pin-pin connections. So when you've got point loads that go in between the panel points, that applies some bending. So that needs to be considered. Fortunately, there's been some research done. So the rule of thumb here is anything that's under 100 pounds, you don't really need to worry about it. Actually, you don't. That's in the standard. You don't need to worry about it from a cord bending perspective. If you have more than that, though, then you got to start thinking. So first step, usually, so the Steel Joist Institute, or SJI, they're the ones who write the standard for steel joist. They'll give you different methods to take that into account. So the main method here is you're going to basically look at the capacity of a steel joist in terms of uniform load, because that's how they're specified. And you can back calculate what's the allowable shear, what's the allowable moment based on these allowable line loads. And that's actually what we do behind the scenes in ClearCalcs. So we'll go through that in a couple minutes here when we do the examples. But basically, you're going to make sure that your loads, your bending moment, and your shear fit within the capacity envelope. So that's typically how you'll find your size. Then what you can do, is you can specify what's called an add load or a bend check. So super short story here. Add load means you're adding a load at any panel point. So at where the webs meet along the truss. So it could be at any single one of them. So the manufacturer will take that into account when they're designing, making sure that the joist is the right strength. Then the bend check is you're actually putting a point load anywhere along the cord. So bending, talked about trusses, bending. Obviously, if you've got bending in the cord, you need that to be reinforced or something like that. So that, in that case, the manufacturer might just beef up the cord so it can take the bending, or sometimes reinforce it, whatever that might look like. Other way to do this, I spoke about the 3 different joist types. So we've got K series, LH series, DLH series. The one I didn't mention was KCS series. It's basically a K series joist, except CF stands for constant shear. And the important part here, instead of having a crazy envelope with your shear that you try to fit your loads in, the KCS is basically meant to have a constant shear capacity over the entire length. So wherever your point load is, wherever your non-uniform load is, as long as you fit within that shear capacity, you're fine with the KCS joist. So it makes it simpler, and in a lot of cases, it actually ends up being a more economical option as well. And lastly, another option that you have here is to call what we have a special joist designation here, where there's an example of what that might look like. You would actually go and put every single load that's being applied to that joist. And that way, the manufacturer, when they see this, they can design it to resist those loads specifically. So different options. Would love to hear in the chat, how you've done these in the past, how you've handled non-uniform loads. It's a combination of these. If you've used another method or something like that, share it with us. We'd love to hear about it. Some other challenges now. Big one is stress reversal. So when you've got wind uplift on a roof, for instance, your bottom chord, which is typically in tension, can go into compression. You've got your roof lifting. Compression means buckling, and so that's might mean lower capacity. Another one there, especially when you're starting to have big point loads, close to supports or something like that, you can get stress reversal in your webs. So a web that would typically be in tension can swap into compression, and all of a sudden buckling becomes an issue again. So solutions there, the Steel Joist Institute, they offer a technical guide for uplift conditions, so how you can work with that, how you can accommodate for that. Spoiler alert, usually it means more bracing, but there are quite a few other ways to deal with this. Another big one here, KCS joist, as I mentioned, they're made for constant shear. So they can take the stress reversal, no problem. All the members are made to take the same capacity and tension and compression there. So that's fine. Also, obviously, manufacturers have a lot of expertise here, and every manufacturer in North America usually has a technical support department that can help you navigate these things. Another one there is with services. So we talked about you can run pipes through the open web, something like that. The question that comes up is, well, how big of a pipe can I run through there? So the Steel Joist Institute, they do have some tables of clearances. So I put a little bit snippet there. So for instance, if I have a 14-inch deep joist, I can see I can take up to a 7-inch round duct through the web. I'm reasonably guaranteed. I'd still want to check with the manufacturer, but it's reasonably guaranteed that that's going to fit. So that's something that you might be able to look at as well. That's all in the Steel Joist Institute's manual and specification. And then lastly, for fire protection, so pretty thin steel, often exposed. It's a fire, there's a fire concern here. So again, this is something that with any steel design, you're usually going to have to consider. For steel joists, there's been a lot of research by Underwriters Laboratories, or UL. They've now come up with quite a few kind of standard assemblies that you can use, different coverings, different floor thicknesses, whatever that might be. And they've associated like the 1 hour, 1.5 hour, etc. fire rating. So these are all, again, in the SJI manual. You can see, for instance, if you've got some fireproofing plaster on your joist, that might be enough to get a 1 hour rating or something like that. That's something that you'll want to look at with the Code of Standard Practice there. But that's typically the solution there, and it's made it a little easier for you with those standard assemblies. I'll stop right now just to say, if you have any other challenges, I kind of went with just a couple of them here. There's obviously more challenges. Feel free to share some of those challenges that you've had in the chat with designing these. So I mentioned bracing a little earlier, talking about uplift. That's a pretty big consideration when we're talking about steel joists. So in steel joists, typically your top chord will be holding up a deck or a floor. So that'll prevent your top chord from buckling. So in that way, buckling is less of a concern as a designer, but there are some things to think about. So the biggest one is during construction. So when those joists are going up, before there's any bracing, before the floor is actually, or the decking is attached to those joists, there's nothing preventing them from laterally buckling. That's a big safety concern. And I think OSHA, for instance, has specific standards and requirements for the bracing of those joists. So you'll see oftentimes the diagonal bridging or horizontal bridging, that's to prevent buckling during construction. And the load tables for steel joists will typically have that information as well. When you've got your floor on, or your deck on, there are still considerations. So for instance, again, when there's uplift conditions and your bottom chord goes in compression, you're going to need to brace that. And when you've got, say, a standing seam roof or something like that, that decking might not be enough to actually restrain against buckling. So there would be some requirements there of bracing. Generally, though, it's the same kind of principle as for a regular steel beam. Lateral torsional buckling, you need to brace against that for your capacity. Again, the Steel Joist Institute, they've got basically very prescriptive requirement. This size joist, if you're above this span length, use X amount of braces, kind of thing. If you want, there are like the more complicated formulas you can use to actually calculate your bracing requirements, but typically we'll just use the prescriptive requirement. Okay, quick slide here about specifying these steel joists. So biggest thing, manufacturers across North America, they've typically got, like I said, a technical support department or something like that. They'll typically offer some design tools, some specification examples that you can put in your scope of work or something like that. And typically they'll have a team of engineers on call available to answer your questions or often even to help you with your design. So definitely that's probably the most valuable resource when you're specifying these steel joists. Important thing to note, though, is despite there being quite a few manufacturers, steel joists are a very standardized item in North America. So you're typically going to be specifying it the same way. So that's, again, the Steel Joist Institute's manual kind of gives those details. So oftentimes 16K3 on a drawing with a span length, that might be enough for specifying. You can also, for instance, say if you want a bit more optimal or let the manufacturer decide, you could say, I want a 16-inch deep joist or K-series joist, but then just specify the load. So in this case, for instance, I just gave an example of 200, 100. So 200 total load, 100 pounds per linear foot live load, and then the manufacturer can decide what works best for them. Important thing here, again, uplift is typically considered separately. So you'd want to specify that separately from your original designation. Okay, so we're now at the part for a worked example. So pretty excited to show you, we've got our new steel joist calculator in ClearCalcs. We've reached out to perhaps a few of you before about these steel joists. And so thank you, all of you who've shared your feedback. And I'd love to hear anybody who's on this call, send us an email, send it in the chat. We rely on you to make our calculators better for you. So as we go through this, if you see something that could be done better, please share with us. Okay, so worked example. Basically, we're going to be looking at just a single-story commercial building, and we're going to be designing a steel joist on the roof. Location is going to be in Chicago. So span length, you can see is 21 foot 4 inches and a 4-foot joist spacing. So uniform loads, we're just going to assume a 10 PSF dead load, 20 PSF roof live load, and then for our snow load, we're going to get a ground snow load of 25 PSF. So we'll calculate the actual roof snow load. So I'm going to stop here now and jump into ClearCalcs. So where am I going to go here? Right here. So I'm in ClearCalcs now. So we're just going to put an address in Chicago. I'm just going to type Chicago here just to get, okay, we're going to be in the Chicago Skyway. That works. Hey, anybody from Chicago, you see your house on there? That'd be kind of cool. I'm going to now create a snow load calculator. So just to get our roof snow load. So I'm going to create a new calculation and scroll down to our snow loads calculator. Right now, this one is in beta. So send us your feedback. We're expecting to take this out of beta in the next few weeks. So pretty excited for that, but we'll use it anyways for now. So here we go. So we mentioned a ground snow load of 25 pounds per square foot for Chicago. So I'm going to put 25. Assuming we're in the city, I'm going to change to surface roughness B, which is the most conservative surface roughness. And then similarly for the roof exposure, we're just going to assume simply that it's sheltered. And then thermal condition of the building, we'll assume a warm roof, which again is the more conservative assumption to make. Talking about the horizontal distance from eave to ridge. So that's about half of the building in this case. So I think we said 21 foot 4 inches, just for simplicity's sake, we'll call it 12 feet. And then the roof pitch, I think in the drawing was 2 and 12. You can see here we've got the project default. In this case, we're just going to overwrite this and write 2 and 12. Roof surface type, we'll just call it obstructed for now, just to keep it simple. And right now, we're not going to be considering any snow drifts. So I'm going to remove these. So if I look here now, I can see my flat roof snow load, 21 pounds per square foot. And my slope roof balanced snow is also 21 pounds per square foot. We're also calculating the unbalanced snow load. So you can see I've got the rafter system one. Because we're dealing with steel joists, we're going to not consider this. So we're just going to look at the unbalanced snow load here. So we can see our kind of unbalanced extra is 9.4 PSF, and that's over about 9 feet. Just for this specific example here with the webinar, I'm going to ignore the unbalanced snow load. That's something that we would add in our loads for a steel joist. But just in the interest of time, I'm just going to focus on the balanced snow load here. So I've got my 21 pounds per square foot. I'm now going to go create a steel joist calculation. So add new calculation, and I've got my steel joist here. And we're running this in ASD. So again, this is in beta. Send us your feedback. Part of the reason we're running this webinar while it's in beta is because we want to put this in front of you. We want to hear your feedback. We want to hear, hey, you can do this better before we take it out of beta and we kind of release it as a full-fledged calculator. So again, please send us your feedback. Try it out, check it out. The calculations are accurate in there. It's really just about making sure that we get feedback. And the other thing too is that we're every calculation before getting it out of the beta, we're getting it validated by external team. So I'm gonna hit yes here, and we'll let this load. Okay, so I've got now my steel joist calculator. You can see by default we've got a 16K5. I'm gonna ignore this for now. We're gonna come back to it. So span length. Right now we've got 25 feet. We said it was a 21 foot 4-inch span. So I'm going to type 21 feet plus 4 inches, and you'll see it automatically calculates it. So 21.3 feet. Center to center spacing, 4 feet. So that matches what we had already in the example. So we'll leave that at 4 feet. Next, we'll look at the distributed loads. So in this case, it'll be a roof load. Start location is going to be 0, end location is going to be L. If I see, so the span length, tributary width is going to be 4 feet. That matches the spacing, and you can see it. It's automatically. So if I change this to say 5 feet, it would update here. But I'm going to leave this at 4. Next, load magnitude. So we said 10 pounds per square foot dead load. I'm going to do that here. Roof live load. So I'm going to change that here. That was 20 pounds per square foot. And for my snow load, like I said, we're only going to look at the balanced snow load right now. That was 21 pounds per square foot. We calculated that in our snow loads calculator. So I'm going to put that in. And with that, that's it. Basically, everything else I need to think about is already included. L over 360 for deflection, for instance, all good. So I can see right now I'm passing 27% for bending, 25% for deflection. It's pretty low, so I can probably use a lighter joist. So I'm going to come to the selector here. And you can see the 10K1 is not passing. So I've got the red X here. So that's fine, not passing. If I then go, actually a 12K1, looks like it's enough. So I've got 61%, 62%, 75% for deflection. So I'm going to select that. And I'll see here, if I look at my moment, I'm going to look at these diagrams right now. So this is where in the presentation I was mentioning, comparing the capacity envelope to the load. So if I look at the shear, allowable shears in blue here, and in black is the envelope of all the load combinations possible. So if I look, black is probably the snow plus dead. I can see that it's always within the blue line on both sides of the shear diagram. So that's how I can be concerned or confident that my design is safe here. If I go to moment now, similarly, the blue line is the moment capacity along the span length. And then the gray line here, sorry, I'll move that. The gray line is the maximum moment from any load combination. So again, I can see it's well within the blue line. So I'm confident my design is safe. So with that, I've designed my steel joist for the uniform loads. This is pretty simple as well. I'm sure you've done this before with the load tables, the SJI load tables. This is just a different way where you can see, for instance, with the percentages, it might be faster. Now, one thing I might want to do is once I've got these steel joists are going to be, say, bearing on a steel girder. So I might now go and say, create a new calculation. Let's do a steel beam this time. And we're going to let's just do a generic beam in this case. So I'll create this. And this is our steel beam calculator. So obviously it's got a couple other different parameters. What's important here, let's say right now our default length is 30 feet. Well, let's say we've got let's say it's 34 feet. I'm just making this up here. What's important, and we'll assume it's simply supported, that's all good. Instead of entering these loads manually in PSF, what I'll do is I'll delete this, and I'm actually going to link the reactions from those steel joists. So, whoops. Seems we've got a little bit of a bug here. You'll have to excuse me here. What if we do this one? Okay, so this is going to be a little less efficient. If I had, say, my steel joist here, I can see my reactions here. So 1380 here and here. In this case, I'm just going to do, say, at 4 feet. So I could actually go and say at 4, and then link another one again at, at 8 feet. I'll be honest, you're witnessing a bit of an embarrassing moment for us. Typically, we would actually have this as a line load, so you would only have to do this once, and you wouldn't have to put in every single location. But say if we wanted to, we're gonna cheat here and make our beam a little shorter, just so we can go through this a little faster. Let's make this a 16-foot beam, and let's just do 12, and that'll be it basically. Just ignoring the ones over the supports. Okay, so now I've got my 3 joists, and I've got my my self weight on this girder. Obviously, a W12 by 45 is probably a little strong. So what I can do now is I could go and scroll. If I say put in a maximum depth of 10 inches, I can see even W10 by 33 is good, or I could even go with the W8 by 15. So let's go with a W8 by 15. And so now what that's done is it's brought in the reactions from my joist. And if I wanted to, I could even go now and say the joist to bracing it against lateral torsional buckling. So I'm going to say yes, bracing at point loads. And you see actually my moment capacity has gone down a lot. In this case, actually, let's just do no, just to keep it a bit more interesting with the utilization. And apologies for the little whoopsie with the linking there. But that's basically it, right? So we've started from our snow load here. We've got a 21 PSF for the roof. We put that on our joists. We found a 12K1 works well for this. And then we can link it to our girder and bring in the loads to that girder automatically as well. So I'm going to stop here for that one. Now let's go back to our examples. So second part now. Ooh, we've got a new challenge. Same joist, but now we've got a rooftop unit that's going on our joist. I'm sure a lot of you have seen this condition before, or you need to decide, okay, how am I going to deal with this rooftop unit on my joist? So we're going to go through this together now. And so if I look here, my rooftop unit, let's see, it weighs 2,000 pounds. It's 50 inches by 114 inches. If I look how it's placed on the plan here, I can see it's spanning over 2 joists. So I'm going to divide that 2,000 pounds by 1,000 pounds. We might also want to just keep it 2,000 if you think, say, the center of gravity might not align or something like that. But in this case, we'll just do 1,000 pounds. Other things to consider here, where it is. And it looks like my dimension line didn't show up, but we're going to say it's at 9 feet from the edge of the joist. So now let's go back to our example in ClearCalcs. So I said, I'm in my girder, so I'm going to go back to my joist. I'm going to now go to the point and moment loads area, and I'm going to type rooftop unit. And I said this was at 9 feet from the start of the joist. And load magnitudes, I'm going to put this as a dead load. So I'm going to put in 1,000 pounds. And that's it. I've put in my loads, but I can see now, ooh, I'm no longer passing that weight. I'm now overstressed for my joist. So if I look at my diagrams, again, the blue line is the capacity of the thing, and then the black line here is the actual, the worst case moment. I can see right at the middle there, it's sticking out a little bit past the blue line, so I know that I'm failing in moment here. And if I look at shear, for instance, again, I can see right around here, the black line is peeking out over the blue line. So I know that I'm failing in shear as well. So what do? Actually, it's quite simple. All I got to do here, I can go to my member selector again, and I can just go and find what works. So I can see there that I had a 12K1. If I wanted to stay within a 12-inch joist, a 12K5 will work. And it'll go from, say, 5 pounds per linear foot to 7 pounds per linear foot. If I'm okay with a little bit more depth, I could even go, say, a 14K4, that's a little lighter, or even a 16K3, which is even lighter. In this case, let's say we want to stick with the 12-inch depth. So I'm going to just pick the 12K5. And that's it. So now if I look, I can see my moment capacity is it's well above the actual moment loads. And similarly, my shear capacity, it's very close, right? And we can see this, it's really like right nearby it. But if I look, we're at 96% utilization. So we're good. And if I look here, I can see maximum utilization per moment, 63% at about 9 feet, right where my rooftop unit is. And for shear, 96% at about 8 feet. And then we'll give you the warning there. The point load's about above 100 pounds, so you're probably going to need to add a extra web member or some local reinforcement there for that point load. So with that said, I can go back now, and if I look, ooh, I've got a red X next to this beam now. And so that's because of our load linking. So because we linked those loads, as I think a lot of you ClearCalcs users are going to be familiar with, it automatically updates the loads on that girder. So I can see now I've got a much higher dead load being applied to that girder. And the 8x15 isn't working anymore. So I might go back now, and if I look, looks like a 8x18 will do the job. So I might just do that, and now I'm good. Now I'm happy. My girder's passing again. So I've got that going. If I wanted to get even a bit more accurate or more thorough with this example, I could now go and say create the snowdrift calculation here. So if I go for snowdrift on projections and parapets, I could do rooftop unit here, length of roof, I think we said 22 feet, and then the step height. So I can click on here. Tara brought this up at the start of the webinar. We'll show you the description here, and we've also got a nice picture to help you out here. So H in this case is the height of the roof projection. And actually, if I look at this diagram, I actually got my roof length wrong. The LU should be probably the distance from the roof to the projection. So I'm going to change this to 9 feet, since that's what we knew from the diagram. And if I go back to the presentation here, I can see the height of this thing is 84 inches here, or 85 inches, let's call it. So I'm going to go back to my table here and type in 85 inches. So now I come here and I'll see my snowdrift height on projections. I can open this and get a picture kind of explaining what's going on here, and I can see the formulas that were used to calculate it. I'm going to close this, just I can't quite see with the presentation screen, but the important ones for me here, snowdrift pressure is 8.74 PSF. So that's the load that gets added on top of the normal snow load, and the width of the snowdrift is 2 feet. So I'm going to add this now. And again, I'm not being as thorough as I probably would be if this was a real design, but just for the sake of time and for the example, I'm now going to create a distributed load. So I'm going to say snowdrift. Start location, I'm going to type in 9 feet minus the length of our snowdrift. So if I come back here, it's, let's say 2 feet. So 9 feet minus 2 feet. And then this is where it gets interesting. So actually, and I'm going to swap these actually. I'm going to do 7 feet and 9 feet. And this is where it gets interesting. This tributary width here, normally we would make this equal to the center to center spacing of the joist. Now, because it's a triangular load, what we can do to make our life a little easier with the triangular load, I'm going to put in a 0 here. And then at the end tributary width, I'm going to put 4 feet. So that's our spacing. And I can actually type in spacing, and it'll take in that 4 foot spacing. And then for the load magnitude, I'm going to go here. I'm going to select a snow load. And if I remember correctly, I think it was about 9 PSF for the snow drift load. So now that this is done, I can see I've got my triangular load here. So I've got my rooftop unit, and then I've got the triangular load being applied. So from 0 to 36 pounds per linear foot from the snow load. I can see now that I've added it, I'm still passing, right? Shear just went up, bending went up a little bit, but I'm still passing. So life's good. Doing it more thoroughly, I'd probably look at the snowdrift from the other side as well. But just again, in the interest of time, we'll skip that part. But that's basically how I'd be doing that. And you can see my B1 here. It's all in the clear as well, right? So I can see if I hover, I'm at 69% utilization. Because my loads are linked, I'm confident that the this calculation, the 69% is calculated with the most accurate, including the snowdrift that I just added. So I'm happy with that. I've basically done my design. So that's basically it for the example here. I see there's a few questions in the chat. I'll take a second here. Maybe if you've got any questions about this example or the previous one, maybe post them in the chat now while I've got this open. Happy to kind of go through this together. Ryan asked, is there a way to sort by weight which would correlate by selecting for economical sections? Ryan, I'm really happy you asked that. It's a really good question. We're actually right in the middle of kind of redoing our selector here. So being able to sort by weight is definitely something that we've heard from quite a few of you. So something that we'll be looking to add. And some of you might have been reached out to already about sitting down with us for a bit of an interview to understand this a bit better. And Pete asked, is the 9-foot measured to the center of the unit? Pete, you're right. I took a couple shortcuts here. I just called it 9 foot. Typically, say for your snowdrift, you might kind of accommodate for that. Or if you had, say, 2 legs for your units, you might split the weight between the 2 legs and put them in as individual point loads. Again, I took a couple shortcuts here. I'll own that part. But that was just for the example. And it looks like that's it for the questions. So I'm going to go back to our presentation now, and we're going to keep going. Actually, the conclusion slide didn't make it. Oops. Okay. We're going to make this the question period. Anybody got questions about the examples, about clear calcs, about steel joists in general? Would be happy to try and answer them and go through them. We've got a question from Pete here asking, does the governing limit include the safety factor? Yes, that's correct. So actually, Pete, I'm glad you asked that. I'm going to go back to clear calc. So what we're doing here, and I'll show you, all we're doing is we're getting from, if you've ever used the Steel Joist Institute's load tables, they basically tell you for this size joist, this span length, this is your allowable line load in pounds per linear foot. And they'll have 2 values. First one is based on the strength of the joist, and then the other one is for deflection. The deflection is basically what's the line load that's going to give you L over 360 deflection. So the one based on strength, that already includes the safety factors. So that's published by the Steel Joist Institute. That already includes the safety factors. So we're using this data directly from the Steel Joist Institute. So yes, it does include the safety factors. So this is the value that we use to create those shear and moment envelopes that you see in the blue lines here. I hope that answers your question, Pete. Let me know if there's anything else I can add here. Thank you. Okay, good. Glad that answered it. Not seeing any other questions right now, and that's perfectly fine. If you've got anything that comes to your mind, please post them in the chat, or even better, put them in our Blueprint community. And I see Tara just posted the link there, so that's awesome. And I see Mike just sent a question here. Does the calculator address floor vibration, or is that a matter of limiting deflection? Great question, Mike. We don't explicitly address vibration in this calculator. Right now, I think that's basically, we're considering that through deflection. I'm very conscious, though, that I think deflection criteria for vibration tend to not necessarily lead to the best results sometimes. Mike, I'd love to hear a bit more about how you're typically doing that in your designs, addressing vibration with steel joists. If you want to, if you'd want to unmute yourself and speak a little bit about this, would love to hear it. Otherwise, if you want to post in the chat, that's also fine. Okay, I'm gonna guess that Mike, you don't feel like unmuting yourself. All good. But thanks for the question. That was a really great question. Okay, so like I said, keep posting your questions. I'm going to go through another slide here. We'd like to introduce our spooky Halloween challenge from ClearCalc. So basically, this is an experiment. Again, we're running our Blueprint community. Pretty excited for it. We'd love to get more of you in there. So one thing that we'd like to do for Halloween, love to hear about a bit of call it a spooky project that you've worked on before. So even better if it had to do with like a haunted house or something, that'd be pretty cool. But more generally, I think maybe what's a project that scared you a little bit, maybe push you a little bit out of your comfort zone. You know, maybe it was a new material, maybe it was a new or unusual loading or something like that. Whatever that might be, we'd love to hear about it. Love to hear, why it was scary, why it was challenging. Love to understand a bit more about that. And I think people in our Blueprint community will be happy to kind of be able to relate to those challenges you faced. And obviously, we'd love to hear how you solved it. Hopefully you did. Would love to see that. And ideally, if you can post some pictures. I know me personally, I love seeing pictures of projects. There's always something cool about them. There's always something exciting about a project, especially when it's a spooky project and there's some surprises that come up. Pictures usually show that well. And the fun part is, if you post this on our Blueprint community, we're going to have a bit of a contest here to send you some ClearCalc swag. So I think, what do we say here? A ClearCalc t-shirt. I got a couple of these myself. They're pretty comfortable. So I'm sure you want one too. But really, this is all about, we'd love to hear from you, from your projects, your challenges. So please, Tara posted the link in the chat for the Halloween challenge. Go make your post. We'd love to hear about it. And with that, I'll mention we've got a webinar coming up in a couple of weeks now. This will be with Atlas Tube. So Atlas Tube, one of the biggest, if not the biggest, manufacturers of HSS. So square hollow sections or rectangular, circular hollow sections. They will be working with us to present on specifying HSS and applying it in structural design. That will be on November 15, same time as this one. So November 15, same time. Would really encourage you to sign up. I'm really excited for that one. Atlas Tubes, they're the experts in HSS. So a lot to learn from them. So really excited for that. And I'm not seeing any more questions. So I'm going to say with that, thanks a lot for coming. I hope that this was helpful. I hope that this was interesting. We will be sending out a recording of the webinar to everyone, and usually we'll have it on our YouTube channel as well if you want to take a look at that. If you have more questions, if you have any comments, if you have any thoughts that occur to you later on, love to see those in our Blueprint community. I hope you had a chance to create an account. And hey, I think leaving you with 8 minutes to spare, it takes less than 8 minutes to create a Blueprint account. So just gonna throw that out there. So I'd love to see you guys out there and chat with you and get to know you and learn about your work and your challenges. So please sign up. Last thing here, would love to have your responses. You're going to see a survey when you leave this webinar. This is just the way that the platform works. If you want us to be able to send you a PDH certificate, we're going to need you to fill out that survey. And then that way you'll be able to get your certificate, and also helps us learn how to make these webinars better. So thank you all, everyone. Really appreciate your time. Really appreciate your participation here. I'm going to wish you a great rest of your day. Thank you, everyone.
Thank you.